May I start? May I start? Okay. Good afternoon for everyone. It's a great pleasure for me to announce the today's seminar is by Karel Proesmans from University of Luxembourg. Just a brief history about him. He concluded his PhD in 2017 under the supervision by Professor Christian van den Broek. He is in his third postdoctoral. Actually, he's currently in the University of Luxembourg under the supervision by Maximilian Esposito. And previously, he developed a postdoc in the University of Hasselt in Belgium, and after in University of Vancouver. It's a great pleasure again for me announce him. It's a very good collaborator, and I have learned a lot from him. So he will talking about finite-time Landauer principle. Karel, you can start when you want.
Okay, so can everyone see my screen?
Yes.
Okay. So first of all, thanks for the very nice introduction, and also thanks for organizing the seminar series. I also was here last time, and it was a very interesting talk. So thanks, and also thanks for giving me the opportunity to talk to you today. And what I will talk about is about some research that I did during my time at Simon Fraser University in Vancouver under supervision of John Beckhofer, also in collaboration with another postdoc, Yannick Erich. Which is about a finite time generalization of the classical Landauer's principle. And of course, if I want to talk about finite time Landauer principle, I first have to say a few things about Landauer's principle. I'm sure that many of you already have heard of this, but let me just give a very brief introduction. In its original formulation, Landauer stated that there is a thermodynamic cost associated with the processing of information. So when you have a computer consists of bits, of course. And if you want to do a computation or suggest the erasure of a bit, there's an inherent thermodynamic cost associated with this. And particularly, when you look at the simple bits, the cost associated with the erasure of this bit. So for example, initially you don't know whether it's in state 0 or state 1, and you want to go to a state where it's with certainty in state 0 or in state 1, then the minimum amount of work needed to do this is given by kT log 2, where K is the Boltzmann constant, T is the temperature of the environment. So this has, of course, a lot of implications. For example, philosophically, it means that there's a deep connection between thermodynamics and information theory. But it also might have some practical importance because, of course, when you look at modern computers, they are becoming more and more efficient, and they consume a lot of energy. And the question is like, how much and how efficient can you do computations on your computer? This might have some, especially in the future, will have some a lot of practical implications. Now, one thing one should say about Landauer's principle is that if you want to reach the Landauer limit, this can only be done if you do it arbitrarily slow. It's a bit like when you have an engine and you want to reach Carnot efficiency. This can only be done in the quasi-static limit. Similarly, if you want to erase a bit and you want to minimize the cost, you can only reach Landauer's limit in the quasi-static limit. So the question we were asking ourselves is, to what extent can you generalize Landauer's principle to finite time erasure? So in the sense that if I have this bit and it's initially, you don't know in which state it is, and you want to fix the state to state 0, and I give you, for example, 10 seconds to do this, is there, similar to the original Landauer bound, is there a minimum amount of work needed to complete this process given a fix in a finite amount of time? And of course, you might wonder, does this have any practical relevance? Because like when you look at real computers, the cost of bit erasure is significantly higher than Landauer's limit at this point in time. In fact, about 1 million times higher. But then when you look at the evolution over time, you see that there has been exponential growth in the efficiency of computations over the last 8 years or so. And that you see that the cost to erase a bit halves more or less every 2 years, roughly. This principle is known as Kumis law. And if you would extrapolate this to the future, you would expect that Landauer's bound will be reached somewhere between 2040 and 2050. So in that sense, over the next couple of decades, you will really start pushing the limit of Landauer's principle. And so it's relevant to know, like, if you want to do a computation fast, how much work is the minimum amount of work needed, and are there protocols that minimize this amount of work needed to do computations, for example, on your computer. So let me just say a few words about the assumptions that I'm making. So generally, when you think about the bit, it's in state 0 or state 1, but there's an underlying dynamics, and there can be a coordinate x, so just a magnetization of, for example, also in experiments, they used real colloidal particles where you'll get the position of colloidal particle. And then, so you coarse grain from this microscopic variable to a macroscopic variable. So instead of a positional coordinate or a magnetization, which can essentially be everything, you go to state 0 or state 1. And so, for example, if you look at a position, you can say, like, if the position is smaller than 0, it's in state 0. If the position is larger than 0, it's in state 1. Or of a magnetization, if there's any magnetization lower than 0, it's in state 0. If it has a magnetization higher than 0, it's in state 1. And initially, we assume that you have an equilibrium state, which means that it's equally likely to be in both states. So it's equally likely to be in state 0 and to be in state 1. And we now want to do some kind of process on this, which makes sure that at the end of some protocol, so at time tf, the probability to be in state 0 is 1 minus, or in state 1 is 1 minus epsilon, and the probability to be in state 0 is epsilon, where epsilon is some small number. So we allow for some kind of erasure error, that there's a finite probability epsilon to be in the wrong state. You can let epsilon go to 0 and then go back to the original Landauer principle, but you can also, in a lot of realistic applications, there is a small chance of having a miscalculation, so to say. And so anyway, to make this more explicit, we will model the system as a one-dimensional overdamped Fokker-Planck equation. So there are some assumptions behind this. First of all, that you can map this as a Fokker-Planck equation. You can mainly think about spatial particles, which is done in like optimal experiments of Landauer's principle, where you, for example, get a colloidal particle and try to erase this by changing its position. But also, like, magnetic systems can be mapped on very similar equations as this, so the conclusion would also hold for them. And also, there's the assumption of overdamped and one-dimensional. This is just for simplicity, but everything that I will say can actually be extrapolated to underdamped system, can also be extrapolated to higher dimensional system. One thing that I don't know whether it can be extrapolated to is quantum mechanical systems. That's something I won't be talking about. So we're assuming classical systems, but apart from that, the results that I'm about to show you are quite general. Okay. So, and also what we now assume is that you have this Fokker-Planck equation, and that you have this temperature and this potential energy landscape. This can be a spatial energy landscape. This can be, for example, be created by optical tweezers, but also by magnets. But one thing that we will assume is that you have full control of the potential energy landscape, which means that at any point in time, you can specify any potential energy at any place along the system. So for any x or for any possible magnetization. And this in turn means that at any point in time, you can create any probability distribution p of x and t that you want. Because when I say, like, okay, we have an initial and final distribution, and I want this part, for example, I want at any point of t, I can specify a probability distribution, then you can show that it's always possible to create a time-dependent potential energy landscape that creates this energy landscape by inverting this previous Fokker-Planck equation. And so this means that full control over the potential also means full control over the probability distribution of the bit. And therefore, it's always possible to erase the bit completely if you have full control over the potential energy landscape. So of course, to do this bit erasure, we will look at the general theory of stochastic thermodynamics. And one general property is that the amount of work needed to erase a bit is always equal to the free energy difference between the initial and the final state, plus the amount of dissipation entropy that is being produced towards the process multiplied by the temperature of the environment. This is just a basic thermodynamic formula, which holds for a broad class of systems. And so this means that to calculate the work needed to erase the bit, which we know should be higher than Landauer's limit, we need to calculate the free energy difference between the initial and the final microscopic state, and we need to calculate the amount of dissipation to go from this initial to this final state. And so that's what's needed to calculate the minimum of work and therefore a generalization of Landauer's principle. Now, the first of these two terms, the non-equilibrium free energy difference, is actually quite easy to calculate, because once you know the initial state and you know the final state, then you can just calculate the free energy difference. I mean, the free energy is just a state variable, so so it's rather easy to calculate. And because we assume that the system is initially in equilibrium, it has equal probability between state 0 and state 1, and more particularly the microscopic distribution is assumed to be the Boltzmann distribution, then you can show that the free energy difference between the initial and the final state satisfies this formula, which you might actually recognize because it's just the Kullback-Leibler divergence between the initial and the final state of the system. So that's something easy to calculate, but the amount of dissipation is way more difficult to calculate, in particular because it's spot dependent. So in other words, if I give you the initial state of the system and I give you the final state of the system, then it is still, you cannot know the amount of entropy that's being produced to go from the initial to the final state, because there are many ways to go from the initial to the final state, and each of them will have a different amount of dissipation in them. However, there is this mathematical theory of optimal transport theory, and Benamou and Brenier about 20 years ago derived this theorem in a much broader context, but specified to stochastic thermodynamics. It actually tells you that if you have an isothermal process and you want to go from initial to a final state, just generally, this also goes beyond Landauer's principle, but just if you have a microscopic system with initial and final state, then you can show that the amount of dissipation is always bounded from below by the quantity that you see here. This quantity is known as the Wasserstein distance. I showed here for one-dimensional system. It can be extended to a higher dimensional system, but the formula becomes way more complicated. But for one-dimensional system, it satisfies this relation. And the nice thing about this theorem also is that it gives you a way to calculate the amount of dissipation, the optimal trajectory. So in other words, it does not only give you minimum amount of dissipation to go from initial to a final microscopic state, it also gives you the amount of dissipation needed, I mean the exact trajectory to go from this initial to the final state. Another thing that's remarkable about this formula is that it tells you that the dissipation needed to do a process in a finite amount of time is inversely proportional to the amount of time that you get. So this is something you see a lot in stochastic thermodynamics. For example, when you do a linear response theory, you can see that if you fix trajectory, it also goes as 1 over t, and also, for example, in the low dissipation limit, and there are several limits. And this is something you see very often, that the amount of dissipation scales is 1 over t. And interestingly, also, this can actually kind of explain this, because this tells you that the optimal trajectory, for the optimal trajectory, the dissipation always scales as 1 over t. So that's one thing we can use, and so this means we have a formula for the free energy difference, and we have a formula for the minimum amount of dissipation to do the erasure. And by putting these together, this gives you a formula for the minimum amount of work to go from an initial state Pi of x to a final state Pf of x. But of course, what we're talking about here is the microscopic distribution. So instead of telling you, like, we have an initial state which has equal probability to be in state 0 and in state 1, and we now go to a final state where the probability to be in state 0 is 1 minus epsilon, and probability to be in state 1 is epsilon. We now have a formula that gives you the minimum amount of work to go from an initial microscopic distribution to a final microscopic distribution. But to minimize the amount of work needed to erase a bit, you actually need to do a second optimization, because you need to optimize of all final distributions that satisfy our constraint, and our constraint is that that the amount of work needed to do, I mean, the constraint is that the probability that your bit is on state 0, so 0 is 1 minus epsilon. So in other words, we don't have a constraint on the microscopic distribution, but only on the macroscopic distribution. And this max constraint also implies a constraint on the microscopic distribution. And so we now need to do a second optimization of this minimum work of all final microscopic distributions. And so you can do this using Lagrangian techniques, but then when you look at it, I didn't go through the calculations here, but I didn't show the calculations here. You can find them in my paper. I can come back to it at the end of the talk. But when you look at this, you get a highly nonlinear differential equation, which even for simplest cases, for example, for a flat potential well or anything like that, it cannot be solved analytically. So it's not possible to exactly calculate the final microscopic distribution analytically that minimize amount of work needed to raise a bit. But what you can do is you can derive a lower bound because you have two terms here. So the first term is the free energy difference, and the second term is the amount of dissipation. And so you can say like, okay, the minimum of the sum is always larger than the sum of the minima. So you can say like, okay, I first minimize the first term over the final distribution, and I separately minimize the second term over all final distributions, and this will give you a lower bound on the erasure of a bit, and also a finite-time Landauer principle. And the result is shown here. So for finite erasure error, you get this rather complicated formula. So the first part, the ln2 plus epsilon ln epsilon plus 1 minus epsilon ln 1 minus epsilon, essentially comes from free energy difference and is just a finite time generalization of the classical Landauer limit. A finite erasure generalization, finite error generalization, which is well known in the literature. And then the second term is an integral which depends on the initial distribution and is inversely proportional to the time, as we already said before. But so now particularly interesting is the case of zero erasure error, of course, because that's also the case when you're thinking about Landauer's principle. That's really the case you're thinking about. And when you look at that specific case, you can show that you get the minimum amount of work needed to raise a bit is equal to log 2, which is Landauer's limit as it is well known, plus the variance of the initial microscopic distribution divided by 2 times the diffusion coefficient times the duration of the protocol. So this gives you a very simple, elegant result, which gives you a lower bound to a finite erasure error of a bit. And you can show that, so it's just, if you know the diffusion coefficient of the system, you know the variance of the system, and you fix the duration of the protocol, you can calculate the minimum cost to fully erase the bit. But the question, of course, is this bound tight? Because, of course, it might be, like I said, it's not, you can never reach this minimum in general. But the question is, can you get very close to it? Because if you're always off by, say, a factor 10, then it's not that useful anymore. But luckily, if you have full control over the potential, you can also calculate an upper bound to the amount of work needed to raise a bit. So there's a rather complicated mathematical construction that we used here. I won't go through the details of that, but you can show that for finite erasure error, that the minimum amount of work is always smaller than, again, the same term from the free energy, plus a second term, which kind of is similar because it also depends on the variance and diffusion coefficient. And in particular, when you go to this zero erasure error limit, you can see that, again, you find the KT log 2, but now instead of variance divided by 2 times d times t, you now get 2 times the variance times d divided by d times t. So in other words, you have a lower bound and an upper bound, and the upper bound is 4 times larger than the lower bound. So this gives you the idea that if you have full control over potential, this is an important constraint, but it's the only, I would say, the only really important constraint. But once you have full control over potential, you can estimate the minimal cost associated with the erasure of a computational bit just by looking at the initial probability distribution and the duration and fixing the diffusion coefficient and the erasure and the duration of the erasure. So yeah, that's, I would say, is the first main result that I wanted to present to you. But as I also mentioned, this Benamou-Brenier theory, which we're building our work on, not only gives you a lower bound on the cost to finish a protocol, but it also gives you a protocol to do this. So let's now look at a simple example. So I will show you now for a rather slow erasure and a rather fast erasure, the optimal protocol. So here, red is always the potential energy landscape, and green is the greenest probability distribution. So you see that the probability distribution is an equilibrium, and you have two obvious well and a way small probability distribution in between them. And we know they'll calculate the optimal protocol to go from this state, which is where there's a 1/2 probability to be in state 0 and 1/2 probability to be in state 1, to go to a distribution where you are always in state 0. So this is the movie, and what you can see is you slowly start pushing inwards the probability, and at the same time, at the end, you start lowering the well, and then you can see that it's a rather smooth process where the final probability distribution also looks very similar to the initial probability distribution, but only on one side of the well. So when you would compare it to the initial distribution, it's kind of similar. And also, when you look at potential energy landscape, you can see that it's kind of similar to the potential energy landscape of the initial distribution. And but again, only on one side of probability distribution, and you push everything inward, and then there's no probability left to be in state 1. So in other words, you complete the erasure. And it looks quantitatively quite different for the fast erasure limit, because here I show you the fast erasure limit, and this first screenshot is like from the moment the distribution starts, and you can already see that the red curve here, so potential energy landscape, immediately pushes up. So at the time you start, you immediately push up the energy landscape, and you just push everything from the right well to the left, and you just let it slide. And it also doesn't really come close to the left well, but it just is pushed over the border, and you don't care about anything else than just, you know, getting it over the border. So for example, if you would think about the magnetic system, if you want to erase it slowly, you just push it slowly, and you will make sure that it's always end up in strongly magnetized to the left. While here, you essentially would just demagnetize it and just push it just far enough that in the long-term limit, it will relax to correct magnetization. But the protocol is essentially finished by just demagnetizing it and just giving it a magnetization epsilon in the right direction. So it's quantitatively very different. And also, I mean, you might start wondering about things like how easy is this to do this in an experimental system. This is something we're currently looking into. But there are all kinds of technicalities associated with this. But you can show that it's quite close to the Landauer limit, to the finite-time Landauer limit. In fact, you can show that in the fast-time limit, you will start saturating this finite-time Landauer limit that I showed you earlier. But I will come back to that in a minute. Another thing that I already briefly mentioned, I will first come back to this. So these are some simulations that we did, where on the x-axis is the duration of the protocol, and on the y-axis is the cost of the erasure minus log 2. So obviously, we know that there's this kind of 1/2 limit, and we have the upper and the lower bound here, and we have plotted it for several curves with different barrier heights. So you have you have a double well system for the potential energy landscape, and you can show that in the slow erasure limit, the cost will also depend on the details of potential, and you can show that the higher the well, the more it costs to do the erasure, but it's not a very strong dependence. I mean, it's always the same order of magnitude. And what you can see is in the fast erasure limit, you can see that all curves converge to the same, and they also all converge to this lower bound. So you saturate the finite-time Landauer principle like the variance divided by 2 times d times t, independent of the details of the system. You always go to the same cost once you do the erasure very fast. So in the slow-time erasure limit, it kind of depends on the details, like the barrier heights. You cannot fully determine the cost associated with erasure. purely by looking at these few quantities like the variance and the d and t, you can get a good estimate because you have the upper and the lower bound. You can see that they always fall within this limit. But in the fast erasure limit, you can really get the exact minimal cost associated with bit erasure just from the few quantities of the system. Now, another thing that I briefly want to touch upon is that over the last decade or so, there have been several experimental tests of Landauer principle. These weren't really done on computers, but mainly with colloidal particles, where you kind of trap colloidal particles in double well system, and initially you don't know in which well system it is. But then you do some protocol which makes sure you end up in the right well. And they managed to verify Landauer's principle, and in particular, they can show that you get this log2 plus a component inversely proportional to the duration of the protocol. But this coefficient, which is inversely proportional to inversely proportional to the duration of the protocol, is different for different experiments. So as you can see here, I'll show you some numbers from different experiments, and we compare them with our minimum bound, which can be calculated exactly because we fix potentials. And you can see that it's roughly like less than 1 order of magnitude difference, but there's still a factor 5 difference associated with the cost of the erasure, depending on which exact experiments. But so by optimizing the protocol further, you can still do better than current state-of-the-art experiments is essentially the message from this slide. So that's kind of finished the first part of my talk. I now want to move to the second main part of my talk, because there's a little trick around this, which she thought about, because we're asking ourselves, like, is there any way, disregarding things like quantum effects, that you can build an engine which, for example, doesn't have this one, or build a bit which doesn't have this one over t scaling associated with the erasure cost? And turned out that in a certain limit, there is a way around this. And the way around this is based on this concept called majority logic decoding. So in majority logic decoding, every bit consists of a number of subbits. So here, for example, we have bits consisting of 5 subbits, and the state of the full bit is determined by the state of the majority of the subbits. So in the first example, for example, you have 3 subbits up, so in state 1, so therefore the bit is in state 1. In the second example, you have four bits pointing down, so we say that the majority of subbits is in state -1, so therefore we say that the bit itself is in state -1. And so you can do some calculation about this. You can calculate the probability of the full bit from determining from the probability of subbits. So if you say that we have every bit consists of n subbits, and every of this n subbits has a probability epsilon to be in state 1, and probability 1 minus epsilon to be in state -1, or in state 0. So then you can calculate the exact probability to be in state 0 from as the sum, but of course the sum is rather complicated to work with. Also, one thing I forgot to mention later, should briefly mention, is that we are assuming that n is odd, so the total number of subbits is odd, because if it's even, for example, if you have a bit consisting of 4 subbits, then there's a fine probability that 2 of subbits will be in state 1, 2 of subbits will be in state 0, so then you cannot really determine the state of the full bits. But if you don't take this into account, then you can always, I mean, if you make sure that the number of subbits is odd, then you can always determine the state of the full bit by looking at the subbits. And anyway, you get this rather complicated formula, but I want to make it a bit easier. So I want to go to the limit in which every bit consists over a very large number of subbits, so say 100 or 1,000 subbits. And then you can look at this formula, rewrite it as an integral, and do some saddle point approximation. And then you can show that if you have a large number of n of subbits, and every subbit is in state 0 with probability epsilon, then the state of the subbits is in state 0 with this probability. And you can show that, so this will always be in state 0 or in state 1, unless you have a 1 over 2 epsilon. 1 over 2 minus epsilon will scale as the square root of n. So in other words, the probability for each of subits to be in state 1 should be 1 over 2 minus some constant proportional to the square root of the number of bits. So in other words, you only need to raise each of the subits by a very tiny amount. So they have almost equal probability to be in state 0 and in state 1. But because you have such a large number of them, the probability of the full bit will still be in state 0 with a high probability, with essentially probability 1. If you do it like this. So we can repeat the scheme for this, and we can try to calculate the minimum amount of work needed to raise majority logic bits. But to go through the calculations, I need to briefly introduce a concept from the mathematical framework of optimal transport theory, which is the so-called transport map, and which depends on the initial and final microscopic distribution, as I introduced them before. So we look at the cumulative initial and final distribution, and then the transport map essentially is the function that mapped the initial probability distribution over final distribution. So in other words, you have some probability which was initially at say x equal to say 0.5, but of course you want to map this to a final distribution where it's in state 0, so x smaller than 0. Then for example, you want to push it to x is equal to minus 0.5, then you would have that gamma of 0.5 would be minus 0.5, for example. Now, of course, when you think about the majority logic in the large n limit, like I said, you barely have to do anything to each subit, but you just have to have a lot of subits. So this means that the final state will be very close to initial state, and that in turn means that you transport everything to something very nearby, or gamma x is equal to x plus some small constant, which is inversely proportional to the square root of n. And then we can look at the minimum amount of work needed to do the erasure by fixing the initial and the final distribution. And fixing the final distribution is equivalent to fixing the transport map. And so that's what we do here. So we write the minimum amount of work in terms of the microscopic transport map. And this is shown in this first equation. And then again, you can ask the same question as before. We now have done the first optimization, namely we have fixed the initial and final distribution, and we have minimized the total amount of work needed to do this. But you again need to do the second optimization of minimizing the final distribution. So minimizing gamma x instead of the pf of x here. And also, you have this constraint, like previously the constraint was the cumulative distribution at 0 was 1 minus epsilon, of the probability that x is smaller than 0 in the final distribution is 1 minus epsilon. Here you can map this on constraint on transport map, which is given here. So this gamma 1 of 0, which is related to transport map, should satisfy this, and we can now minimize this function again using Lagrangian techniques overall transport maps, and this gives you this differential equation. And in contrast to the previous one, this equation can actually be solved exactly for several cases, or at least be written as some kind of series expansion or anything like that. For example, flat wells, you can solve it exactly. So this is a nice technicality of the majority logic decoding, that in contrast to the single unit bits, this majority logic bits, you can determine the optimal protocols analytically. Okay, so let's first look at the slow erasure limit and compare the minimum cost of majority logic with single unit bits. So ML stands for majority logic, SU for single unit bits, in terms of the epsilon of the full bit. So this is here epsilon stands for the full bit and not for the subbits in the majority logic decoding, and for the classical single unit bits, it doesn't matter. And what you immediately see is that independent of the details of the system, you can calculate the cost associated with this. And you can see that the single unit bits are always easier to raise than the majority logic bits. So this kind of doesn't sound very good, because like, why would you use majority logic if single unit bits are better than the majority logic bits? But you get a completely different story when you look at the fast erasure limit. Because in the fast erasure limit, you can see that minimum amount of work to erase a majority logic bit, scales as 1 over the square root of those, so 1 over the square root of the duration of the protocol, while the cost of erasing a single unit bit scales inversely proportional to the duration of the protocol. So if tau becomes very small, if the duration of the erasure becomes very short, then you can show that the scaling of the majority logic bits is superior to the scaling of single unit bits, and therefore majority logic bits will work better than single unit bits. Like I said, in the slow erasure limit, the single unit bits will be better. So which kind of bit you want to use essentially also depends on the kind of tasks that you want to perform. But for fast erasure, majority logic bits are better. For slow erasure, single unit bits are better. Now there's a little catch here, because initially I told you like you always have this 1 over those t scaling. Here you have the 1 over square root of t scaling, so that sounds a bit strange. And the reason for that is that I already have taken the limits of n going to infinity before taking short erasure limits. So we are assuming that the number of subbits is essentially infinite, which is never strictly true. So this 1 over square root of those scaling will stop at some point, and you will go back to 1 over t scaling, but still in this limit, you can still see that you have this inverse proportionality to the square root of n. So still in this limit, this majority logic bits will work better than the classical single unit bits. And as an example, let us look at the flat well. So essentially you trap the particle in a flat well, and between some two extremes, xs minus L or xsL, and the bit can be everywhere with equal probabilities initially, and then you push it, you again make a protocol that pushes the bits to the left-hand side of the well, both for majority logic and for single unit bits. So we assume here that there's a finite erasure error probability, which will be like 10%. So 10% of bits will be erased in the wrong space, but we can still look at the erasure. And so here we have looked at several distributions. So the black curve is is n is equal to 1. So every bit has 1 subit, which is just a classical single unit bit. And the blue curve is the majority logic decoding. And the other ones are essentially 3, 9, 33, and 99. So what you can see is that that indeed if you do the erasure slowly, then the single unit bits will be better. And essentially the rule is the less subbits you have, the least costly the erasure bit is. But when you go to very fast erasure, things completely change. And what you see is that at small scales, essentially the rule, it's kind of the inverse. Like the more subbits you have, the easier the erasure comes. And already if you have like 100 subbits, you already have the superior scaling of majority logic bits to single unit bits. So this gives you an idea that it is indeed true that majority logic decoding can be better if you want to do fast erasure than single unit bits, even though the superior scaling of the 1 of square root of tau will only hold up to a finite duration. This shows you that this duration is actually very short, and that will hold even if you have a relatively low number of bits, like say 33, you can already see that you can perform single unit bits up to a rather short time. Okay, so this brings me to the end of my talk. So I would say that there are the main takeaway messages that we have looked at generalizations of Landauer principle to finite duration of protocols. And not only have we given lower bounds to erase a bit, but we also have derived optimal protocols to do this erasure. And derives this Finite-time Landauer principle, which is quite simple in terms of the initial probability distribution of system. And then the second part of my talk, I showed you that there's this technique called majority logic decoding, which in certain limits can outperform single units bits. And if you want to know more about my work, there are 3 publications. The first 2 are mainly on the first part of my talk. The third is on the second part of my talk, and here are the references. And I would welcome any questions. Thanks.
Karel, thank you very much. Thank you very much for your very nice talk. Now we are open for some questions. Would you like to ask something?
Hi Fiore, Gabriel here. What's up?
Okay, good. You can ask him.
Hi, yeah, may I start? Hi Karel, thank you for the talk. My internet connection was a bit unstable during the middle, so maybe I missed something. I actually have two questions. So the first one is the Benamou-Brenier bound that you kind of start with. Do you know which process saturates that bound? I mean, is it known?
Yeah. So it's kind of hard to explain. It's like when you have the cumulative distribution of the initial and the final process, it's essentially you just linearly extrapolate over time between the initial and the final distribution. It's not, it takes some getting used to, and it's not that easy to write in a simple formula. That's why I didn't put it down here, but you can show that you can derive it. And yeah, if you want, I can send you the original paper of them in which they actually show it. Yeah.
Okay, I understand. And then maybe my second question is, so when you showed the zero erasure error, maybe a few slides afterwards, yeah. So maybe this is not applicable here, but could one make some considerations about the size of the system? I'm wondering, like, how would this minimum work cost change if the system goes from microscopic to macroscopic or something like that?
How do you mean by going from microscopic to macroscopic?
So I was wondering somehow if I understood correctly, you're assuming that the variable x is maybe like a colloidal particle, right?
Yeah, something like that.
Yeah. So somehow could there be a mass there that would make this a very large particle, or could maybe we have something like a collection of such particles and so on? Would that change anything? Because the first term seems to be intensive, and the second term is the variance, which is extensive. So that's what I was wondering.
Yes, I see what you mean. I'm not entirely sure. It's a good question. Not sure if I can really answer it.
No, it's okay. Maybe it doesn't apply to this case because it's just one particle. But okay, cool. Thank you.
More questions?
Oh.
Ask him, please.
Okay. And so, Karel, you are looking at a bound for the work. You are looking at the minimal work. And I wonder what happens to the... If you repeat the process, you have a fluctuating work, right? So what happens to the probability of the work?
We haven't looked into that. It's an interesting question. I think that you will, especially in the fast erasure limits, I think that there will be a lot of fluctuations in the work, because when you get this protocol, you have like this potential energy landscape becomes very big. So you essentially dissipate a lot, of course, because like the work, like I said, it essentially diverges. And I think that the fluctuations in the work will become big, probably. But we have not really looked into that too much. The thing is that this framework of Benamou and Brenier is only applicable to very specific sets of problems, so you cannot really calculate the for example, minimize work fluctuations with it, or not in a very direct way. And yeah, so I don't really know anything about like variance or high moment. But I think that in slow erasure limits they will go to zero, in the high erasure limit they will become very big.
Okay, thank you.
Karel, I have one question. In the case of the majority code, how do you choose the neighborhood? You consider how do you consider the majority for taking in that case n equals to 5? You select n5 in that example, in that picture, 5 spins, and you count the spin of the neighborhood, or do you consider another thing?
Yeah, so every bit consists of a number of sub-bits. So here, every bit essentially consists of 5 separate bits. So every sub-bit only is associated with one major bit. And so then you just look at state of each of these subits. And here, for example, in the first example, you see that there are more states in state up, so in state 1. And in this one, you see that there are more states pointing down, so in states -1. So that determines the state of the full bit.
Okay, but in the case of large, what is large? The number of bits, the
number of
n, large.
So here you have 5 subits, but now you could also look at systems which say 10,000 subits, and that's the large n limit.
Okay. So second question. You summarized some boundaries in the end of your talk. So
this one?
Sorry, maybe. No. You have compared the 3 cases you have considering. Let me see. Maybe the next. I don't know. But I don't know if my question makes sense. But according to your examples, what would be the simplest case for erasing a bit?
I think you mean the simplest toy model for bit erasure?
Yes.
Yeah, I think it's essentially this one. So this is also a model that has been studied before, for example, by Zulkowski and Deweese. And essentially you just say like, okay, you have this particle in a box which can move between 2 boundaries at x's minus L and x's L and can move freely within these boundaries. And then you can say like, okay, initially there is a infinitely thin border in the middle, so that essentially it's equally likely everywhere, but it cannot jump between state 0 and 1. And then when you start your protocol, you immediately remove this border and you just let it interact in any way, and then you put some potential energy landscape, and then at the end you put the border again. But essentially, like in the causal systems that I study, the only thing that you fix is the potential energy distribution. And I would say that a flat potential energy distribution is always the simplest. Now, I would say that there are also, for example, coarse-grained systems, or also when you look at quantum mechanical systems, you often go to discrete state systems. Then you could start looking at 2-level systems with some kind of rates between them. And then things are different. Then that would be in a certain sense easier, but I would say that this framework is not applicable to that. And as long as you don't look at quantum mechanical systems, these 2-level systems are also just some coarse-grained version of this more general class of systems.
Okay. Any more questions? No? Karel, let's thank him again, Karel Proesmans. Thank you very much. It's a great pleasure for me to have you here. And